Understanding arc length in polar form is essential for fields like orbital mechanics and engineering. When a particle's distance from a center point changes as it rotates, calculating the total distance traveled requires a transition from simple geometry to integral calculus. By the end of this video, you will be able to derive and apply the polar arc length formula with ease. Before we begin the derivation, remember the bridge between coordinate systems. Any point in the plane can be represented by its distance from the origin, r, and its angle from the positive x-axis, theta. These conversion equations, x equals a cosine theta and y equals a sine theta, are the starting point for our derivation today. Recall the arc length formula in rectangular coordinates. We approximate a tiny segment of the curve, ds, as the hypotenuse of a right triangle with sides dx and dy. This gives us the differential arc length ds equals the square root of dx squared plus dy squared. Our goal is to transform this expression entirely into terms of r and theta. Since r is a function of theta, when we differentiate x and y with respect to theta, we must apply the product rule. This step is crucial because it allows us to express the change in x and y as functions of the radius and the rate at which the radius changes with respect to the angle. Let's begin the derivation. Starting with x equals a cosine theta, we take the derivative with respect to theta. Using the product rule, we get dr d theta times cosine theta, plus r times the derivative of cosine, which is negative sine theta. This represents how the horizontal position changes as the angle increases. We do the same for the y-coordinate. Starting with y equals r sine theta, the derivative with respect to theta gives us dr d theta times sine theta, plus r times the derivative of sine, which is cosine theta. We now have expressions for both dx d theta and dy d theta. To find the arc length, we need the sum of the squares of these derivatives. Squaring the expression for dx d theta involves expanding a binomial, which gives us three terms: a squared term for the derivative of r, a cross-product term involving both r and its derivative, and a squared term for r. Now we square the expression for dy d theta. Notice the symmetry between this and the previous result. When we add the squares of dx d theta and dy d theta together, the complex middle terms, the cross products, are identical but have opposite signs, meaning they will cancel each other out entirely. We have found that the rate of change of the arc length squared is simply r squared plus the derivative of r with respect to theta squared. This is the polar version of the Pythagorean theorem. It tells us that the total change in distance depends on both the radial distance and the rate of radial expansion. By taking the square root and integrating with respect to theta from an initial angle alpha to a final angle beta, we arrive at the final arc length formula for polar curves. This elegant integral allows us to find the length of any continuous polar function without ever needing to convert back to x and y. Let's test this formula on a simple circle with radius 3. Since the radius is constant, the derivative of r with respect to theta is 0. Our formula should simplify to the standard geometric formula for circumference that we already know and trust. Plugging r equals 3 and dr d theta equals 0 into the integral, we get the integral of the square root of 9, which is 3. Integrating 3 from 0 to 2 pi gives us 6 pi. This perfectly matches the geometric circumference formula, 2 pi times the radius, confirming our derivation works. Now let's try a more interesting shape, the cardioid, defined by r equals 1 plus cosine theta. To find its total length, we first calculate the derivative, which is negative sine theta. We will integrate from 0 to 2 pi to cover the entire shape. Inside the square root, we square the radius and the derivative. Expanding 1 plus cosine squared gives us 1 plus 2 cosine theta plus cosine squared theta. Adding the sine squared theta term allows us to use the Pythagorean identity again, simplifying the secant to 2 plus 2 cosine theta. To solve this integral, we use the half-angle identity. 2 plus 2 cosine theta is equivalent to 4 cosine squared of theta over 2. Taking the square root, we get 2 times the absolute value of cosine of theta over 2. Because of symmetry, we can integrate from 0 to pi and double the result. The integral of 2 cosine of theta over 2 is 4 sine of theta over 2. Evaluating from 0 to pi gives us 4 minus 0, which is 4. Doubling this for the full cardioid results in a total arc length of exactly 8 units. This shows how powerful the formula is for non-trivial shapes. consider the logarithmic spiral, often found in nature. Here, r equals e to the power of a theta. The derivative is simply a times e to the a theta. When we plug these into our arc length formula, we find that the terms factor out very cleanly, allowing for an easy integration of an exponential function. What happens if r is negative? In polar coordinates, a negative r simply means the point is plotted in the opposite direction. Since the formula uses r squared, the negative sign is squared away, meaning the arc length formula remains valid even when the radius passes through the origin. A common trap is choosing the wrong integration bounds. For example, the curve r equals sine theta completes a full circle between 0 and pi. If you integrate from 0 to 2 pi, you will calculate the arc length twice, resulting in a distance double the actual circumference. Always check the period of your function. The most common mistake is confusing the arc length of a curve with the arc length of a circular sector. The simple formula s equals r theta only works if the radius is constant. For any changing radius, you must include the dr d theta term to account for the radial movement. Be careful with your algebra inside the square root. You are adding the squares of two separate quantities, not squaring their sum. Also, ensure you apply the product rule correctly when finding the derivatives of x and y during the derivation process. To summarize, finding the arc length of a polar curve follows a consistent four-step process. First, find the derivative of the radius. Second, square both the radius and the derivative. Third, add them and simplify using trig identities. Finally, integrate the square root of that sum over your chosen angular interval. The polar arc length formula is a beautiful extension of the Pythagorean theorem into the world of rotation. It captures how a point moves both around the origin and away from it simultaneously. Mastering this formula opens the door to understanding complex motion in physics and engineering. Let's test your knowledge. If r equals theta squared, what would the integrand for the arc length be? Think about the derivative of theta squared and how it fits into the formula. I'll give you a moment to decide between options A and B. The correct answer is B. Since r is theta squared, its square is theta to the fourth. The derivative is 2 theta, and its square is 4 theta squared. Adding these inside the square root gives us the correct integrand. You can even factor out a theta to simplify it further before integrating. You now have the tools to measure the paths of the most intricate shapes in the polar plane. Practice with different functions to become comfortable with the trigonometric simplifications that often arise. Thank you for learning with us today. Generated by Vision Solve AI.